Assalamualaikum warahmatullahi wabarakatuh, and a very good day. So now we will continue with mass balance, chapter 4.4, which is regarding balance on reactive process. Okay, so what we are going to learn here is we have two topic learning outcomes. The first one is to perform material balance calculations for a reactive system using extent of reaction, atomic, and molecular methods. Secondly, is to perform material balance calculations for a reactive systems involving recycle and purging streams. So in previous lesson, we have actually learned part of the first topic learning outcome, where we have already know how to solve a material balance using extent of reaction. So in this lesson, we're gonna know about the relationship with atomic and molecular methods. Okay, so for balances on atomic and molecular species, these are another methods that we can use to solve mass balance. Before this, we have already learned two ways to solve mass balance. Let's say, for example, we have here A reacted with B to get C. So the first method is the simplest one, where we just simply create a table. So how do we create a table? We just need the information from the question. First of all, we need to know the initial mole of all compound. That would mean reactant A, B, and C. So we have to write how much is reactant A, B, and C. From there, we can actually know which one is limiting reactant and which one is the excess reactant. And then by knowing the limiting and excess reactant, we can actually calculate how much A and B reacted. So here we have how much reacted. From there, we will also know how much C is produced. So we will know how much A reacted, how much B reacted, and how much C produced. From all of this information, we can know the final value. So what do we do? For the reactant, we just deduct the initial with the react, how much it is reacted. While for the product, whatever initially we have, we will add up with how much generated. Then we will know how much is the final output. From there, we can calculate the final composition of the output. So that's the first method, which is the simplest method. Then we learn about the second method, where we solve the mass balance using the extent of reaction. In this case, we're going to use the balance using extent of reaction through the formula of mole of any species at the output. So here is O means output is equals to mole of that species initially. So as the input. So here is input. Here is output. And then we have either plus or minus. It will be plus if it is a product generated. It will be minus if it is consumed or reacted. Then we have to add the stoichiometric coefficient, and we have to include the extent of reaction. By writing down the equation or extent of reaction for each species, we can solve the mass balance. So that's what we have learned so far. So now we're going to learn about how do we solve mass balance using molecular species and atomic species. So by the name itself, balances of atomic species means we're gonna count on the number of atom itself. So what is atomic species? That would be, for example, only N for nitrogen, C for carbon, H for hydrogen, and then O for oxygen. And what is molecular species? So molecular species is basically a molecule or a compound. Like here we have N2, we have methane here, CH4, and we have nitric oxide here, NO. So solving mass balance means we have to write the balances. So we already know what is the equation representing the extent of reaction for mass balance. Now, how about the balances on molecular species and balances of atomic species? Here, for molecular balance, which means balances using molecular species, we're going to use the standard general mass balance. We know that the standard general mass balance is input minus output plus generation minus consumption is equals to accumulation. And if the situation is steady state, then accumulation will be equals to 0. So rearranging this new equation, we will get input plus generation equals to output plus consumption. So that's basically the molecular balance. Then we have, how do we solve mass balance using atomic species? Okay, atomic species is more interesting. As you know, for atomic balance, it is simply input is equal to output. There will be no generation or consumption of atom due to the law of the conservative of mass. For you to remember, it's as simple as when you write the chemical equation. Let's say, for example, you have C2H6 dehydrogenate to become C2H4 plus hydrogen. We can see here the input consists of 2 carbon and 6 hydrogen. So the balance for carbon is okay. And then for the output, we have here carbon is the same, 2. And hydrogen is 4 plus 2. We got 6. So for carbon input, there is 2. Output, there is also 2. Similarly, for hydrogen input, we have 6, while the output we have 4 plus 2, which is equals to 6. Okay, so that's just like a general information. Okay, now let's see how do we solve the mass balance. So remember, part of the process in solving a mass balance is for us to find the degree of freedom, to know whether a situation, a question, a problem is solvable or not. So what is the basic equation for degree of freedom? So we have here degree of freedom is equals to number of unknown minus number of independent balance. Let's say here equation lah. Equations representing the independent balance minus any specification given by the question. So how do we count number of independent balance? So in this case, for molecular and also atomic species, there are few rules that we have to take note on. The first one is, if two molecular or atomic species are in the same ratio to each other where they appear in a process, which means input and output both have the same ratio, balances on those species will not be independent. Let's say we have two species and in the inlet they have same ratio and in the outlet has same ratio. So we will represent it as only one independent balance. So only one independent molecular or atomic species balance can be written. So this is referring to the balance lah, the equation. Secondly, chemical reactions are independent if the stoichiometry equation of any one of them cannot be obtained by adding or subtracting multiples of the stoichiometric equations of the others. Okay, let's see an example. Here we have a mixer. So we know basically a mixer doesn't involve a reaction, right? It's just gonna mix whatever in. Okay, here we have two input. The first one is air. Second one is methane. Methane is represented by CH4. Let's say that we represent the amount as N2. And then for air, air is basically a ratio of oxygen and nitrogen. So we have here oxygen and also nitrogen. And how much is oxygen and nitrogen? Let's say we don't know how much was the inlet. We can represent it with N1 and 3.76 N1. Where does this 3.76 come from? We know that generally in air, it consists of 21% of oxygen and 79% of nitrogen. So how much is the ratio between nitrogen and oxygen? That will be 79 over 21. Or we can write 0.79 over 0.21, and that will be equals to 3.76. So this is how we got this 3.76. So how much oxygen there is, let's say we have N1 oxygen, then there should be 3.76 times N1 of nitrogen because of the ratio that always consistent in air. So the product, how much is the product? The product now we have three components, which are oxygen and nitrogen, and finally we have the methane lah, the one that we mix together. So we don't know the methane, we can represent it with N4. Oxygen, we don't know, we represent it with N3. Now nitrogen, we won't represent it with a new number like N5 or new variable. Instead, we can represent it with 3.76 N3. So you can see here that we have reduced the number of unknown because oxygen and nitrogen are interdependent. It depends on each other. Because of it has the same ratio, we can represent them also with only one balance, one equation. Okay. All right, let's see here. Molecular, also atomic nitrogen and oxygen are always in the same ratio. This is what I have explained previously. Since in air, we have 21% of oxygen and 79% of nitrogen. So notice here we have 79% of nitrogen. So we have here nitrogen in the form of N2. And also we have here 21% of oxygen in the form of O2. So when we divide them, we got 3.76. So in terms of molecular balance, we have this ratio. How about in terms of atomic balance? So we have here 2 and 2. So the balance for atom is also the same. For every oxygen, let's say because we multiply this by 2 and multiply this by 2, we can actually exclude it. So for every atom of oxygen, there will be 3.76 atom of nitrogen. As if you are writing like 2 times 79 over 2 times 21 and also O. So we can remove this and we'll still get the same thing, which is 3.76. The same case applies to methane. So here methane, we have CH4 before it was mixed. And after it was mixed, it's also methane lah, CH4. So for every 4 hydrogen atom, there will only be one carbon. Okay. Therefore, for this situation, when we have a mixture of two input, which are the air and also methane, to get a result of three component, there is only two independent molecular species, which are, first one is CH4. So this is representing molecular, okay? So molecular balance, first balance will be the balance representing CH4. Second balance will be one balance representing either oxygen or nitrogen. So in total, 1 plus 1, we get 2. Similarly, only two independent atomic species. So one, either C or H, because C and H, the ratio before and after mixing is always the same. Before, it exists as atom, it exists as methane. So for each 4 hydrogen atom, there should be one carbon. And the output is also the same thing. So we can represent it as one equation. And then we have here oxygen and nitrogen as the same thing because of the consistent ratio here. So we have only two independent molecular species, so two balances also can be written, only two independent atomic species. So in the end also, you can write the two independent balance. So the others, so we can only choose one lah for this couple and choose one for this couple or this couple. So this represents the equation and also the independent species. Okay, let's see an example. Let's say we have here a mixture of ethylene and nitrogen is fed to a reactor in which ethylene is dimerized to butene. So here we have an inlet of 100 mole per second. And then we have ethylene here. So we have ethylene 0.6 mole per mole C2H4. So that's the fraction. Then we have nitrogen here. Mole fraction is 0.4 mole and 2 per mole out of this 100 mole per second. And then it was fed into a reactor. So a reaction happened. What happened? There was a conversion of ethylene into butene. So 2C2H4 is converted into C4H8. And then we got the output. So here the output, we got a three component. First one is the unreacted material, which is C2H4. Then we have the product C4H8 and also the the component that is inert, not involved in the reaction, which is nitrogen. Okay, so we have three components lah. Now, how many independent molecular species are involved in the process? How many independent molecular species? And show your analysis and list down all molecular species balances. Okay. Here, we have three independent molecular balances. We have C2H4, we have C4H8, and also we have nitrogen. Because the ratio for molecule here is not consistent lah. So here we have three independent molecular species, so no problem. But how many independent atomic species are involved in the process? Okay, this time, now we will see the atomic balance. Because molecular balance, no issue. Now we see the atomic balance. So here, notice nitrogen, we have no issue lah. Nitrogen, we can have the one atomic balance representing nitrogen. And then how about C and H? Yeah, we have three atoms in total. We have C, H, and nitrogen. So, and no problem. But how about C and H? Does it have a relationship with each other? So let's see here. The input, we have C2H4. So for every C, every one C, there will be two H for the input. For the output, for every one C, there will be also two H. Because the ratio here is 2 to 4, 4 to 8 is equals to 1 to 2 ratio. Because of that, we only have two independent atomic species balances. One is nitrogen, no issue. Another would be either carbon or hydrogen. Why? Because the ratio is consistent for the input and output. See here, ratio 1 to 2, here also ratio to 2. Yeah, I hope that is clear for you. Okay. Now here are the guidelines to solving mass balance of reactive process. Which method will we choose will be basically based on this guideline lah. When will we choose atomic species balance to solve the mass balance? Generally, we use it when for the atomic species balance generally lead to the most straightforward solution procedure. So this is the simplest one. We actually prefer atomic species balance, especially when more than one reaction is involved. Usually we favor this method lah. The easiest one is simply input is equals to output, the balance. Second is extent of reaction. So this extent of reaction are convenient for chemical equilibrium problems when equations solving software is to be used. That means it's usually a more complex equation lah. There will be more than one reaction involved, so there are several extent of reactions. So we basically will use software to help us to solve the mass balance. And thirdly, molecular species balance require more complex calculation than either of the two approach, either of these two approach, and should be used only for systems involving one reaction. Because of this method is more complicated in terms of calculation. So if we have only one reaction, then yeah, we can try molecular species balance. But if we have more than one reaction, we better try different approach, which are either atomic species balances or extents of reaction. Okay, let's see one example here. We have mass balance analysis. This is just a simple recap back of what we have done so far, but using an example. Let's say we have a dehydrogenation of ethane. So we have here C2H6, dehydrogenate to get C2H4 and also hydrogen. And we have an input here 100 mole per second C2H6. So after the reaction, we will get three components. The first one will be the unreacted material, which is C2H6, the excess of the reactant. Then we have the product, which are C2H4 and also hydrogen. Let's say we already know that the input is 100 mole per second, while for the output, we only know for hydrogen, which is 40 mole per second hydrogen. So we can use either approach, either we solve using extent of reaction, atomic species balances, or molecular species balances. So for extent of reaction, remember back the method, we have to do it for all species, where for all species, output is equals to input plus or minus V extent. For example, here we have three components. So for first component, C2H6, here we have C2H6, that will be, the output will be N1, which we don't know, equals to the input we do know, which is 100. So C2H6 is a reactant, so minus. And here we have only 1, the stoichiometric coefficient, so 1. Then we have extent, so that's one equation. Then we have for the product, C2H4. So here product, the output of the product is N2. The input, we don't have any C2H4 in the input, so that will be 0 lah. It's a product. C2H4 is a product, so plus. And here we have one stoichiometric coefficient, so it's 1. Then we have extent. So N1 is equals to 100 minus extent. N2 is equals to the extent. And finally, for hydrogen here, the output is 40. Input is 0 lah, because there is no hydrogen here. So here is 0 hydrogen, 0 C2H4. So no input. And then hydrogen is a reactant, so plus. And then here is 1, the coefficient, so 1. Then we have extent. So now automatically we solve that the extent is equals to 40. Knowing that the extent is equals to 40, we can know what is N2. So N2 is equals to extent, which is 40 lah. Then we can also solve for N1. So N1 is equals to 100 minus extent. So here we have N2 is equals to 40. Extent is 40. So 100 minus 40 equals to 60. So that one is the method for extent of reaction. Then we can do also using atomic species balances and also molecular species balances. So atomic species balances is very simple equation. Simply input equals to output, but you have to do it for the atom, for hydrogen or for carbon. Okay. Then another one will be molecular species balances, which is the equation will be input plus generation equals to output plus consumption. So we will learn more detail in the example. Okay, what is the general strategies to solving mass balance of a reactive process? So first, we read the problem and we identify which method is appropriate. Let's say it cannot be solved using table for some reason. Then you can choose either you can solve it through extent of reaction, atomic species balances, or molecular species balances. Remember, molecular species balances usually we use it when when we treat only one reaction. And extent of reaction and atomic balance we can use for all. After we identify which method we want to use, then we have to perform degree of freedom. We know that degree of freedom is equals to number of unknown minus number of independent balance or equation minus number of specification. Don't forget from when you are doing the degree of freedom, don't forget to identify also your limiting and excess reactant. And finally, you can solve the unknown that have relationship with the given information, which is the specification lah. We have process specification given such as fractional conversion, excess air to oxygen, etc. And we can solve the mass balance. Okay, so we will continue in the next lesson. Thank you very much. Thank you very much, everyone.